All right, let's do it.
Okay, so first thing, can you tell us a little bit about your research in your lab?
Yeah, so we just moved to Northwestern with the whole team. I have been though at UCSB 19 years, so obviously we have been doing this for a while, but moving gives us an opportunity to really focus and refocus to do the research that we think will have the most impact and is the most fun. So I'll tell you a little bit about snippets of the research emphasis. So the original home, if you will, is magnetic resonance spectroscopy, both NMR and EPR. But we are really interested in the idea of quantum sensing, and we are actually coining a term, quantum resonance sensing. Quantum sensing has made a big splash by academician as well as industry. And there is this vision that could allow to see things deeper, better at a single molecule level. But all of the quantum sensors, or not all of them, that's not true. A lot of the quantum sensors are spin-based. Magnetic resonance experts know really something about spins, and especially my group has been focusing on dynamic nuclear polarization, which is transferring information and polarization and signal from electron spin to nuclear spin. We know how to match the energy. We know how to tune the spin diffusion barrier. We know how to localize information. We know how to basically fight or mitigate relaxation effects. So this is a really exciting area that we have been in there, but we have the opportunity to really focus on it, right? So we have 3 research topics. One I call design spin cluster for NMR signal amplification and quantum resonance sensing. So it's about really spin physics, spin chemistry, magnetic resonance for the purpose of, I would say, changing the landscape for quantum sensing. In quantum sensing, people are so focused on generating a device that meets the criteria that perhaps there is not enough emphasis on the design of the spin physics itself. So, for example, in DNP, we know that we need to meet resonance condition to detect a nuclear spin or to amplify the nuclear spin signal. E1, E2, those are electron spin. They match the energy by their difference to the nuclear spin. Then the signal amplification is very large. And if you want to detect the information, the range is much larger. In a quantum sensor, if you go to 1 nanometer to 2 nanometer, that's a big deal. A lot of things can be sensed if you could do 2 nanometer sensing. People are really fighting with this 1 nanometer limit. We have recently even developed a new construct. When you utilize clusters of narrow line radical, you have even more power efficiency and even more range. So we are looking for students who are interested in doing the spin design, which is a little bit of even materials or biomolecular assembly design, functionalization, spin physics, theory, magnetic resonance, both NMR and EPR, and instrumentation. So to be really able to focus on the spin design, we will not worry about the initialization. A lot of group focus on optical polarization to have this pure initial state. We are going to use magnetic resonance. We're going to go to high field, 7 Tesla, 2 or 3 Kelvin, just for the purpose of getting a pure state. We can get it in steady state, and then we can worry about the spin physics. So there's a lot of excitement and a lot of research ideas that we can explore. The second topic is water. We are big fans of water, and I think I forgot to say that we are both broad and focused in some sense. We're interested in many things, but at some point I realized in order to have an impact, we do need to focus a bit so that everything we do is building towards a bigger picture and a bigger goal, right? So one important criteria is we would like to look at surfaces and molecules in water. Science in water is very different from a non-aqueous solution, which are equally important, but water is fascinating, and we really have the tools to make a breakthrough in water. And quantum sensing in water is pretty much quantum sensing in biological system. Why should quantum information science and computing not be relevant for brain science and biological science? But an important emphasis has to be how to design spin systems in water. And also a parallel to that goal is understanding fundamental structure of water, right? The reason why heterogeneous catalysis is actually challenging, not directly transferable from homogeneous catalysis, is because the water takes on different structure and surfaces that you wouldn't have in solution state. So we drew this cartoon that might look a little bit like science fiction, but actually we have a very nice recent JAX paper that shows we have this low entropy structured water that gets evicted and facilitates binding. But we have a lot of good evidence. Collectively, we know this is true. What if you could measure it? And so we have a new favorite tool, which is oxygen 17 NMR, together with all these other wonderful tools that we have been measuring. I think we can really have a breakthrough in water science, water structure, by combining that with dynamics measurement theory and also achieve quantum sensing in water. Finally, third topic will sound very applied. Controlling aggregation to generate assemblies of tau that should be therapeutic targets. Now, what are we doing here? There is a grand challenge. So aggregation of tau in specific forms is actually considered, by cryo-EM, it's known that that specific shape is diagnostic. So a doctor will only know definitively somebody passed away from, for example, CTE, after postmortem analyzing tau deposit structure. If that's the case, if it's not true for all protein, but it's true for tau. If that's the case, we should understand and be able to generate these disease-specific fibrils, right? But it's very difficult. Let's take these images, and there's a lot of measurement that we are doing, cryo-EM that we are doing, but accompanied by DIA, that is a very, very good pulse DPR technique to get at solution state structures, as well as solid-state NMR that gets at the dynamic region. But a grand challenge is, how do we make a flexible polymer fold perfectly and stack perfectly? It's really difficult. I mean, try that with, imagine a flexible thing that you're going to fold like that. It would be costing us enormous engineering challenges to get there. But biology knows how to do it. And actually, I would argue nobody knows how it works. We have a hypothesis, which is water. So in order to stack proteins perfectly, you need a site that's like a pin. So imagine you are walking and you're in the dark and you need to find a door. So what do you do? You kind of tap at the wall and there's a door, it will kind of go in, and that's, oh, that's the door. I think something similar is happening with water. The water structure and softness or hardness is different. But that's a very big statement, needs to be measured. And if you can figure out the principle by which proteins stack, that's a big deal. Now, what has quantum sensing and NMR anything to do with it? A lot. Because to measure that water, the only way, in my opinion, to measure that really directly is using spin systems. Oxygen 17 chemical shift tells us about electronic structure. You want to target it, you need a spin label at that location. You want local information, you need to control that your information you want to get goes far enough, but not too far. You want local information, let's say within a nanometer, but not within 5 nanometer, right? So all of that, it's probably a lot of information, but I hope it gives you an idea.
Awesome. think.
Long answer.
And our next question would be, what kind of skills are you looking for in a student to succeed in the lab?
Yes. So magnetic resonance spectroscopy, of course, needs quantum mechanics and quantum physics and spectroscopy, but while having the skills and having that prior knowledge makes it easier for you, you absolutely don't require that to be successful in our lab. What I mean by that is you require that eventually, of course. I mean, entering student. Really what you need is interest. I believe in the idea of character and personality. Everyone is different. Some people are just naturally talented with hardware. I've seen that. Some people are just naturally talented and just interested in synthesis. And some people are naturally drawn to uncovering a puzzle. So that's what we want to do. I want curiosity, commitment, and just interest. That's it. That's all we need. And then, of course, hard work, but the rest follows.
That's great. And then we'll wrap up with one last question. If you want to talk a little bit about your lab culture.
So my lab culture, let me unshare since we don't have to show now the slide when I talk about lab culture. It's a team environment where I take everyone very seriously, but I also expect everyone to respect everyone. Knowledge is not a criteria for respect. Knowledge is good. Knowledge is a tool, but knowledge doesn't make you a better person nor a better scientist, actually. A good scientist is someone who is willing to observe, be open-minded, to work hard, but to also really think outside the box. That's a good scientist. And a good human being is someone who learns how to respect everyone, right? You are an equal value to me. And we play all different roles. We might be professor, student, staff, whatever, doesn't matter. But we all have our values, and that's a very important criteria. And if you kind of view it that way, I would like to argue it's a lot of fun. I really don't think there is a reason to be miserable, if that's what you're asking. That doesn't mean that our lab doesn't sometimes have stress, but that's different. We all pull on one string. We are a team and we are super stressed out. Like when we were moving, oh my God, everyone is so stressed out. We are stressed out, but we don't go against each other, right? We are just stressed out and see what we can do and try to come, like help each other. And, sometimes I say, I need this, I need your help, but it's always like, I need your help, not like you do it. Yeah. That's different. And I feel like that's not only the right thing to do, but it's also very good because I get help too. So it's a very effective as well as good way of being a lab together. And that's what I intend to do at Northwestern.
Great.